place on time. So we have Professor Apurva Patel from IISc Bangalore, and he's going to talk on sensing with waves, classical and quantum. It's going to be a very interesting talk. So let's listen. Apurva.
So thank you, Swapan, for inviting me to this meeting and asking me to give a talk on sensing. And I must admit that I don't really work in this particular area, but I teach the basic concepts in my class. And what I'm going to do is treat all of you as my students in the class and describe those basic concepts, hoping that something interesting or something provoking enough will come out from the discussion. So what I'm going to talk about is how do you use waves for sensing various kind of things, and what are the kind of advantages you can get from that, and how that can be included to make different kind of devices. So yeah, let me also add that there is an effort to develop quantum technology at the Indian Institute of Science, setting up a large enough collaboration, including many different topics with superconducting devices, photonics, communications, and also the theoretical support for it. And it's a collection about 40 different faculty members from probably a dozen different departments. And I am leading that particular effort. That is the way I keep in touch with all kinds of things which are going on. Okay, so now let me start at the basics. Start with sensors, which we all have. And they are both particle sensors and wave sensors. Mouth and nose work as particle sensors. They detect molecules of various different types and figure out what it is. Eyes and ears act as wave sensors, light and sound. And they also detect various things from around the world. What good are they? The important thing to realize that two wave sensors can do what a single one cannot. For example, two eyes estimates distance to the light source by parallax. We have two slightly differing images, and our brain is smart enough to combine them and figure out how much is a shift, and from that shift, decide the distance. Ears do the same thing, but in the time domain. The signals are restored a little bit different in time, and from that we judge the direction from the sound. And this is not possible with a single source. You cannot judge either the distance or the direction if you had only one eye or 1 ear. So somehow natural evolution figured it out. And we have two of the wave sensors and one of the particle sensors. Of course, the other sensor is our skin, but that is in a different class, so I will not go into that detail. So how do you extract this extra information? That you have to combine two separate signals and extract the correlation between them in some manner or the other, and that has new information. And this is the generic principle of using waves to find something which cannot be extracted at all if you do not have multiple signals coming from the same source, or the inverted situation where you have multiple sources but the same detectors. And this we have used in different ways. And the question is, can we expand that library? For example, the GPS, the Global Positioning Systems, uses both space and time separations to fix the space-time location. It does the job of both eyes and ears. And what is needed is you combine them, a very simple consideration from geometry, that in d dimension, you can cover all the points using the structure called simplex, which has d+1 points. And so GPS needs 4 satellites plus our measuring instrument to fix time and space simultaneously. So the questions which one can immediately ask now is, can we put some system of these multiple receivers on our devices which we routinely use? For example, a mobile phone. Can you put multiple sensors and make it more useful? The size of the mobile phone is not very different than the size or the separation between the 2 eyes and 2 ears. Will you be able to get anything new out of it? If you want to look at it atomic scale, you can ask whether this atomic force microscope or the scanning tunneling microscope, you put multiple sensors instead of just one tip. Can you do something more? What more you can learn about the materials and the structures that you want to study? And now this is a sort of motivation. Now let me try to be a little bit more quantitative. I'm not going to be technical at all. So this is all at a very simple, broad picture. Look at the information which you can extract from wave signals. Basically, it has 2 features. One is the intensity and another is the phase. What is contained in the intensity is essentially local and particle-like. You can measure its strength as a real number. But the new stuff which is present in waves is whatever is present in the phases. This phase information is what we play with when you look at multi-part correlations, and that is a novel feature. How has this been used? So astronomers have already explored this thing in a great detail. They use this information in the phase to improve the signal to noise ratio. The characterization is that the range of sensing should be larger than the range of the noise. So if you use large baseline interferometry, you can get rid of local disturbances. So the spatial correlations are spread out over the signals, but you bring them together and combine them in some clever manner to extract that correlation in or the information, and that will help in improving the signal to noise ratio. You also use in the time domain where you take images which have long exposures. And these long exposures are not sequences of individual shots, but you retain the phase information by taking the Fourier transform of the signal in the time domain, and that will filter out unwanted transients, which are short time scale signals. And both these features are built in to the analysis programs of what astronomers do, and they get a good advantage of the signal to noise ratio, giving us fantastic images of galaxies and star clusters and whatever larger structures or the universe there may be, but this is what is routinely done. And what is the mathematics buried inside it? It's quite simple. It is essentially described by this particular properties which electrical communication engineers use. It is called super additivity of communication channels. Essentially, it amounts to saying that if you have two copies of the same object, that state is more distinguishable than just one copy. Mind you, these two copies have to be correlated. So it has to be coming from the same source, whatever it is. And how it is more distinguishable? Well, the distinguishability is governed by state overlap. So you ask what is the state overlap? It is just a dot product. So here is cosine theta. Here, two copies will give you cosine square theta. Cosine square theta is smaller than cos theta. And so the smaller the overlap between the two states, you have higher distinguishability. And if you want to make it better and better, collect more and more copies. That's all. Nothing more complicated than that. So this is what waves can do. And I can point out something else, which is not a property of waves, but which is based on a similar idea. This is again something used by the astronomers, Hanbury-Brown twist interferometry. It doesn't use correlations in phase, but it uses correlations in intensity. And how is that useful? That comes because of another quantum property, which is identical particles. So if you have identical particles, you can still measure intensity and also include multiple paths because they will give the same final state. And the key feature is this multiple path. As long as you have that, they have extra information and that you can use for something which is of your interest. So that is a kind of generic structure of what you can get out of waves. Now let me be more oriented toward quantum mechanics, but still keeping this wave dynamics in the background. So what we know or what we learn in our first course in quantum mechanics that whatever the dynamics is, it has both wave properties and particle properties. And they are all mixed up together. We are told that you can measure one or the other depending on your interest, and there is no problem. So how is this composite structure buried in the quantum information framework that we have developed? That the framework of definition of a quantum state involves both these labels in a different context. Waves are used to construct superposition, which means multiple signals at the same point in space and time. And that I'm calling a zero-dimensional structure. And somehow it is in an internal space. And the particle structure we use as a one-dimensional sequence, as in our language. And it doesn't have to be one-dimensional, but that is the most common structure. Higher dimensional stuff also you can construct. And the mathematical label for that structure is tensor product. We typically use it as an ordered sequence of some letters in the alphabet. And this is how quantum algorithms put together both the structures of waves and particles. And what do we get out of it? That classical algorithms will be restricted to using only the wave or the particle, but not both of them. Quantum algorithms will use both of them simultaneously. And to compare the two, it is kind of useful to figure out how much is coming from one part and how much is coming from the other part. Okay. And that is the quantification, which again can be done easily, and I'm going to describe it next. But let me also tell you that this combination, you put superposition and tensor product together, it produces a property called entanglement. The states cannot be factorized anymore once you have both of them simultaneously present. On the other hand, if you look at only one or the other, say only the wave part, what you don't require is entanglement. Coherence of the phases is sufficient. And you can extract information from that coherent signal. Okay, so now let me jump into what the particles alone can do and what the waves alone can do. So the particle property is discreteness. It essentially is stating the fact that the properties are going to be localized in space and time in some particular form. And if you use this localization in a clever way, the tensor product structure naturally leads to this possibility of factorization. And then that factorization can reduce the resource requirements, and the advantage can be even exponential. And what happened? Okay. Let me just illustrate it with various kind of examples. We use all these things routinely. So we use a digital language with a place value system, or even our written language made up of alphabet. What is it? It is a factorized process where the meaning of a number or meaning of a word is broken up into a sequence of letters. Once you put all of them together, you get the full meaning. But to write them or even talk about them, you will speak one digit or one letter at a time, and that cuts down the resources. That using, say, n digits, you can cover all the numbers from 0 to whatever, 10 raised to n. How we use it in another place is how you look up a word in a dictionary. You don't look for the whole word, you look for the first letter, then the second letter, third letter. So these are the quite common uses of how a computational task can be simplified by breaking up into smaller parts. And the behavior is actually quite generic, and that can be illustrated by just a simple explanation of what will be done in any computation. So consider any Boolean function that is all being handled by our gadgets of various digital devices. The Boolean numbers are only 0 and 1, and they have a nice property that x square equal to x. So you try writing down any function, it breaks down into a multivariate linear polynomial. Nothing more than that. Linear because x square is equal to x. No higher power can appear. And multivariate because you can have many different arguments. You ask how many different possibilities are there. So you can immediately write down this, whether it has one of the x variables, one or two, etc., and you can write down that you can generate 2 raised to n possible terms by writing polynomials in n variables. And in each term, either a particular variable is there or not there. That is how a 2 raised to n number comes in. But what can happen is I want to evaluate this polynomial. What is the best you can do? That is to factorize it completely. Each factor depends on only one of the variables. And if that happens, then here there are 2 raised to n terms. I'm not going to evaluate them one by one. I will multiply these factors together. And there are n factors, and the computation will involve n additions and n multiplication, nothing more than that. The effort is order n. So how much you have gained? Well, here it was 2 raised to n, and here it is n, so you can write the maximum gain. Maximum gain because you have to know this procedure of factorization. It may work, it may not work, but that is the maximum gain achievable in a particle-like implementation. Now let me go to waves. What can you get out of it? So the characteristic property here is superposition, and which means that multiple signals are going to coexist. How can they be used? This is a label from the computer science description. It is called single instruction multiple data. That the superposition of multiple parallel threads can be all processed by a single instruction, transforming all the components in one shot. And if you are able to do that, the resource requirements again will go down, and it's very easy to see that that is an exponential gain. And again, various simple examples. We use it for communications. For example, the broadcast of all the mobile phones, everything goes out together. You will pick out what you want, but the signal which is transmitted has all of them together in superposition. So the advantage now amounts to saying how many states you can superpose. And here is a simple illustration again in the quantum information language, that you can start with a state of n zeros, rotate each one to 0 plus 1 by root 2, and write it out by brute force. What is the result? And it comes out that every sequence of 0 and 1 will appear once in the expanded structure, and there are 2 raised to n terms. They all have equal amplitude because this root 2 is a common for all of them. And so you can produce a uniform superposition of 2 raised to n components by using effort which is n. You either rotate each n of the qubits, or you multiply all of them another effort of n. And so the advantage to produce this superposition again has a factor 2 raised to n divided by the actual computation which you did, which is n. And this is the maximum gain available in a wave-like implementation. Maximal because you are looking for some structure like this, which is uniform superposition. And the fact that this number is the same as in the particle description is something which is worth remembering, that there is as much to gain from the waves as much is there from the particles. There is a caveat which goes with the structure of superposition, and that we have to pay attention to, that when you perform a final measurement, it destroys the superposition, and only n components and n selected properties of those components can be extracted from 2 raised to n superposed components. Again, our mobile phones are a good example. All the signals are there, but your device will pick up only one signal, which it is tuned to. And one has to be clever enough to combine the superposition stuff by interference, amplification, all kind of tricks to be able to achieve that. Then you will get the maximum advantage. So now let's look at quantum algorithms. They use both of these things simultaneously. But the caveat is that the endpoints of our quantum algorithms are the same as in the classical definition on the result of the problems. We can write them down on a piece of paper. So the in-between root is quantum, but not the input and the output. What can we gain out of it? Well, we look for the best strategy, and that is possible if you can exploit both factorization and superposition maximally. It can be done in very specific problems. If you can't do it, then there has to be a trade-off. And the examples of both of these are well known. The algorithm which Peter Shor discovered for finding period of a power of a number is an example where factorization and superposition do not overlap. So you get the maximum out of both the worlds. And that has become a what you call benchmark, or not even benchmark, the leader of all quantum algorithms, and given a tremendous boost to this subject. On the other hand, there is Grover's algorithm, which is also discovered a little bit afterwards. And there is a trade-off that you can get something from factorization, you can get something for superposition, and they are not independent. So you want to combine them, you don't get maximal advantage of both of them. You have to figure out what to put your emphasis on. And of course, both these algorithms have this second feature as well, that the output is concentrated in a few wave modes. Mathematically, it's a situation similar to a delta function, and that is possible in both Shor's and Grover's algorithm. And if you are not able to do that, then the success probability will go down. And the point which I want to just carry forward from this is you have to look at the problem structure. Without that, you cannot really make absolute statements. And now let me go back to the classical domain again and ask some physically relevant questions. One thing which we know already, that quantum dynamics is highly fragile against environmental disturbance, while the classical dynamics can be fairly robust. So can we consider a trade-off between these two as well? That the quantum stuff is not going to work, what should I give up and still get whatever I want reasonably efficiently? And then the answers are quite straightforward. Particle dynamics gives up superposition. That means multiple paths which may contribute, they have to be evaluated one by one, and then the total execution time will go up. If I choose to work with wave dynamics, give up the particle part of it, then I will have to work with capital N coupled oscillators instead of log 2n qubits. And that means that the space resources will go up. Remember, it's time versus space. And still, wave dynamics with coupled oscillators have many nice properties, which are all well known in classical physics, that coupled pendulums synchronize. You may have seen lights hanging from the same wire. Whether you like it or not, they all start moving together. It's very useful in designing algorithms. A simple lens performs Fourier transform. Okay, you don't need really quantum mechanics to do that. Wave optics is good enough. And these are the components which you should know how to put together if you are dealing with waves. They're not complicated, just you have to think in a little bit different directions and see where it takes you. And if I'm now looking at the trade-off, the question will come, what is more affordable between time and space? If I really can't do the quantum stuff, should I go for the particle version or the wave version? And the answer is fairly straightforward, that wave dynamics can be advantageous in situations where spatial resources are cheap, while time is highly precious. And it is in some sense a large-scale parallel computation. If you have cheap resources, you will put a lot of them together to do the same job. And this is a superposition done in a little bit different sense. And what are the examples? Such examples are very commonplace in biological systems. The cheap, redundant spatial resources are deliberately used all over the place. Not just one example, seeds of a plant. One seed has to be enough to carry the next generation. Plant will produce millions of them. Why? And the biology has figured out the answer, natural evolution. What is important is a tiny advantage in time. I want to get there first. I can spend unnecessary energy by many parallel streams, but I want to reach there first. Because reaching there first is the critical success in competition, and that is what evolution is all geared for. And here you don't have to even worry about polynomial, exponential, etc. It is just a straightforward competition. And now look at what goes on in our own body, every living organism. There is a huge amount of parallel computation, no doubt about it. On top of that, all the fundamental processes in every living organisms are at the molecular scale, the metabolism. And what does it do? It does the job of sensing. Detects all kinds of signals, and based on signals carry out some particular tasks. That's it. And how much of that we have understood? Actually, not much. It goes on in our cells, whatever it is. Lots of sensing is there. Lots of processes are there. And one thing which we have known, it does not chemical reaction, but wave dynamics. The molecules vibrate, and their transients created by all those vibrations are very important part in the dynamics. We don't know what is going on, but there is a lot of stuff to learn inside there, even at molecular scale. The question is, I'm back where I started, some biological example. Can we mimic such strategies? And just like our 2 eyes and 2 ears, you don't have to ask questions about how many thousands of these I need. 2 coherent signal streams would be a good start. What extracts you can get by just putting 2 sensing devices together, but making them coherent. And well, that is a food for thought, which I want to give all of you. Thank you very much.
Thank you, Apurva. Thank you. Thank you, Apurva. Great talk. I actually learned that from him. So this is why we were stressing that when we do these nano engineered quantum structures, we need to learn how to coherently create large arrays of them so you can benefit from it. Take one question maybe from the audience before you go on to Oliver. Questions? Oh, okay. Apurva, we have done it. Great. Thank you very much. Right. Yeah, last speaker of the session is Oliver. He's coming all the way from London or Geneva. I don't know where he's coming from today. Geneva. Okay. So he's going to detail out the atomic interferometry efforts and some more.
Okay, yeah, first of all, thank you very much for the invitation. It's a great pleasure to be here as the last speaker now of this quantum sensor session. And I'm going to talk a particular quantum sensor here, namely atom interferometry, and in particular large-scale atom interferometry to explore fundamental physics goals. Before I come to that, I think it is a prudent approach to give a very short introduction to this quantum sensor, which is a relatively special quantum sensor. And as I'm not really coming out of the field historically of cold atoms, I always have tried to find an analogy which I'm familiar with. And the best analogy you can have for atom interferometry, I think, is laser interferometry. That's something we're actually teaching to our students at universities. So most physicists are being familiar with. And in laser interferometry, obviously the active element is laser light, which you shine on a beam splitter. Then you basically have the two different paths which are opening for the laser light, and you reconnect them with mirrors then in the detection system. And what you're measuring then are the light fringes. And from the light fringes, you can deduce whether or not there has something differently happened in the two different paths. That's laser interferometry. That's the technology we have been utilizing to measure gravitational waves so far. Atom interferometry is conceptually very similar. However, now here, the active element is not laser light, but it's atoms. And it's not just one atom. It's actually a cloud of atoms, typically 10 to the 6, 10 to the 8 atoms, which are really cooled down to their ultra coldest possible state. So there's ultra cold atoms. And then you're utilizing laser light to act as a beam splitter. And what then happens is that you're basically separating this cloud of atoms, which is in the absolute ground state, into half of them being in an excited state and the other half of them remaining in the cloud state. And the excited state then travels through space and time, but still being in an entangled state. Now, that's where the entanglement comes in. So it's a true sense quantum sensor. And again, with laser light, you can establish then mirrors where you're turning back the excited state to the ground state and vice versa. And at the end of the day, in your detection system, like for laser interferometry, you are observing matter fringes or atom fringes. Now, this atom fringes then will tell you whether or not something has happened to the phase of the atoms when it was traveling the two different paths. So that's conceptually the idea behind atom interferometry. Obviously, the technical implementation is much more challenging. Now, we have already seen at the beginning of this session quite nicely the comparison of utilizing, instead of an atom interferometer, atomic clocks to basically show how we would like to measure, for example, fundamental physics signals. So this is a slide I actually have stolen from Jason Hogan, as a matter of fact, which I really think makes it very nicely. So again, you have your ground state and your excited state of atoms. So this could, for example, be strontium atoms, as in our case, which are cooled down to the lowest possible temperatures. And then what you do is you use one laser beam to basically synchronize these two clocks. So you have to imagine that these two clocks are really separated far from each other in space-time, or in space, not in time, but in space. And that laser beam is synchronizing them. So with that laser beam, I basically split the atom sample, half of them in the excited state and half of them basically in the ground state. Now I'm starting my experiment. So these clocks are now traveling, wow, okay, there's a lot of a delay because of Zoom in there. Now, traveling through space and time, and I'm again synchronizing my experiment. Now, what happens with the synchronization with one laser beam is, because the excited state has traveled through space and time, and if you write down the simple Lagrangian or Schrödinger equation for that, then you know that There has to be a phase to be accumulated at the excited state. Now that phase, if I compare the two clocks, will be basically related to the frequency difference of the excited and the ground state, in this particular case for single photon transitions. And then if I compare the two clocks, I basically can do a null measurement, because the same phase has been accumulated on clock 1 and on clock 2. If I compare the two clocks in terms of time, I will get a null measurement. However, as already been shown also earlier, what happens if a gravitational wave would penetrate the space-time continuum of one of those clocks? And this is now obviously a conceptual simplification. But what would happen is, because of the strain this gravitational wave carries, there will be a length dilatation, which, because of the speed of light and will translate and basically into a time dilatation this atomic clock is going to see. And that time dilatation is basically being imprinted on that phase. Now, if I again make now the comparison between the two clocks, I can measure back delta t, and out of delta t, then I can basically deduce all the fundamental properties of the gravitational wave that has been there, frequency, and also its strain. That's the idea behind it. Now, as it happened to be, you can do exactly the same thing also for ultralight dark matter. As it has already been introduced, if you think of ultralight dark matter, like for example, as a Bose-Einstein condensate, so it will be described as a classical wave, which is basically penetrating us as we speak. And that classical wave now will introduce some changes to the fundamental constants of the atoms, for example, to the electron mass, but also to the alpha fine structure constant, which you can see as an imprint of an additional frequency on the separation of the ground state and the excited state. So this additional frequency that's been imprinted is basically coming and the property of the dark matter candidate you have, namely its mass. So there's a one-to-one relation between the two. Now that delta omega alpha, again, if there's a cloud penetrating this one atomic clock, will imprint on the phase, but this time not on the time, but actually really on the omega itself. So again, if I'm comparing back the two clocks, I will be able to measure delta omega alpha and hence deduce the properties of the dark matter candidate which has been there. So that's the basic idea behind this. And it's interesting to say that with the same experimental setup, you can be sensitive to gravitational waves, but also to ultralight dark matter. So that's the basics behind it. Now, there's another very interesting thing. For those who are having worked with laser interferometry, they know that in order to measure really gravitational waves, it is always important that you have this two-arm structure, because you basically compare two arms with each other in order to get rid of the laser noise that's been imprinted on your mirrors and everything. That's a fundamental principle of laser interferometry to reach this precision level when it comes to gravitational waves. For atom interferometry, conceptually, you don't have to do this, because the laser beam you're using, or the laser pulse you're using, will obviously have phase noise, mechanical platform noise, and so on. But because of quantum mechanics, you will imprint that on two clocks in the same way, exactly the same way. Again, it will separate and drop out in the difference of your measurement. So that means that conceptually, and that could be an advantage to design the experiments, you don't need a double arm structure, but a single arm is fully sufficient to measure the properties you would like to do if you're utilizing atom interferometry. So that's one thing. Now, ion, and that's the experiment I'm going to talk to initially, is the experiment we have been establishing in the UK, as I will show you in a second, is really a different kind of an atom interferometer. So far, I've introduced to you this with clocks, but it really was meant to be atom interferometer because it has several advantages, but more difficult to explain than the basics behind this. Now, if I want to build an atom interferometer on Earth, then I would like to ensure that I have sufficient amount of free fall time to interrogate the atoms. So basically, and that's been shown here in the space-time diagram, you can go to shafts. And that's been shown here. So there's different variations of shafts we have in mind. So for example, you can build a 10-meter tower as a prototype, then you can scale it to a 100-meter detection system. And eventually, we're planning to build kilometer detectors on Earth, which are having the capability, as I will show you in a minute, to measure gravitational waves. Now, the challenge will be that you really have to push the basic parameters of atom interferometry to a completely different level. And we are very much aware of it, that this really has to be pushed to different parameters. And one of the most optimistic scenarios we found is to really base the atom species on strontium, the single photon transition on strontium. And the reason for that is that there has been a lot of development with atomic and optical clocks, which were based on strontium over the years. I mean, there were enormous improvements on the technology side with atomic clocks, and we are benefiting from that improvement now to translate this over into atom interferometry. But we are very much aware that we have to push the basic parameter space of atom interferometry for this particular species enormously. Now, for that reason, we have really built this 4-stage program in the UK. The first stage, which is to establish the technology and to basically build the expertise across the UK and to build a 10-meter prototype. That stage is now being funded with £10 million. So it's currently ongoing over 30 months, but we're already actively planning for the second stage, namely to put that technology into a 100-meter detector and to build that detector somewhere on European soil. There are several sites we are discussing of how this can be done, and this is actively under consideration here. Stage 3, this will be the ultimate kilometer scale for the terrestrial detector, as I will show you in a minute. This is then when you really go fully in the exploitation of gravitational waves in a new frequency band. But last but not least, and there's another thing we are actively working on, is to bring this to space, because that's the ultimate sensitivity you can reach when you bring this technology up in space. Interrogation time, but also separation of these atom interferometer sequences will be the advantage. But you will have to go through the stage program before you really can put it into stage 4, namely into space. But we have already submitted proposals to ESA and to NASA, who are currently under evaluation related to that for some pre-studies. So that's ongoing. Now, this is the ION collaboration. Just to point out, it's really is a big commitment in the UK. So these are the institutions which are involved in ION. So you can see here, there are all the big players in the UK. So there's Oxford University, there's Cambridge University, there's Imperial College, there's the Quantum Hub in Birmingham, there's Liverpool, and we also have a national lab, namely RAL, being involved. And that's the collaboration we have here. Some people you might be familiar with in particle physics. So John Ellis is one of the funding members as well, like myself. But then there's also people like Ian Shipsey or Daniela, who are coming out of the particle physics community. And as a matter of fact, that collaboration consists out of 50% particle physicists, i.e. those who want to do fundamental physics, and 50% on those who are the technology stakeholders, namely coming from cold atoms. So there's really a merger of two communities that's going to happen. And it's not only a one-way street, you know, that particle physicists are benefiting from quantum technology, but I would also like to show you that we from the particle physics community can bring something to the plate in order to improve the turnaround frequency for quantum technology development. So that is my first lesson we have learned after 18 months. So we're really now 18 months into the project with this 10 million being spent. And one of the big challenges we were facing was to build 5 ultra-cold strontium laboratories across the country. And that was one of the things the funding agency was asking us, and many of the cold atom people were asking us and said, how can you build 5 state-of-the-art ultra-cold strontium laboratories in just 18 months? That was the challenge we were facing. And the answer to that was obviously not when we are pursuing the same technology development cold atom peoples are being used to. We have to employ the methods we have been learning in particle physics, in the large detector production. And that means we have to do centralized design and production, and we have to go to proper management and use the resources we have at our national laboratories. So that was the way forward. And just to cut a long story short, that was quite a successful way. It was initially a painful one because there's 2 cultural things coming together. One is, like myself, being used to work in big teams while cold atom people are just coming from the other way around. But eventually we managed, and we started with a full centralized construction of our ultra-high vacuum system, which is the core of such a cold atom experiment. And you can see here the different stages. So all institutions were being involved. We had centralized engineering efforts, part coming from RAL, from our national labs, but also from Oxford and Imperial College. And this is then how these ultra-cold vacuum systems looking like. Such an ultra-cold vacuum system with that complexity typically takes 4 to 5 years to be built in an individual lab. That's what usually has to be done, because there's many steps you have to do to really bring it to this part. Now, with the centralized production, we were able to basically then build up this in 18 months. So that is one of the things. And we were building strontium labs in Birmingham, Cambridge, Imperial College, Oxford, and RAL. And these are pictures of old strontium labs as they are meant to look like eventually when they're being done. So these are really complex beasts you have to build up. And typically, as I said, it takes 4 to 5 years to have a fully functional lab, depending on the expertise you had. And we had to do 5 of them in 18 months. And just to show you that this is possible, so that was the first delivery of one of the sidearms, which were centralized, produced at Dasbury Laboratories, a national laboratory, to Cambridge. So that happened in July 2022. So the project started in May 2021. So that's even less than 18 months. And this is then how such a system looks like. So this is really the 3-chamber ultra-high vacuum system in which you can do all the strontium interferometry you would like to do. The next delivery then came, this is really slow, to Birmingham in July 2022. You can already see the changes now. So the first one took us 6 months to build. The second one was being built in 5 to 6 weeks, because all the expertise we learned in a centralized place. The third one then came in Imperial, which has a special feature, but I'm not going into this. This is really slow. In August 2022, so just a month later. And then we had basically Oxford delivery in October 2022, because there was the summer break, so some of the production didn't happen. And the last one then was being basically delivered in RAL, also in October 22. So you can see 5 of those ultra-high vacuum systems were being delivered basically in the time frame of, a couple of months, some months. And not only this, because in parallel, we were also delivering laser stabilization system and optic system to these labs. So that means that basically shortly after the delivery, so they got the sidearm in July 2020, they saw the first 2D strontium mod, which is a real commissioning aspect, then already in October 20. The next one then we have seen was in Cambridge on the 26th of October. And then we had basically RAL following it. And Imperial and Oxford have slightly different focuses. They are going directly through the 3D mod, which will take another month longer. But that basically means it is possible now to build these labs in a time frame of a year. And that obviously is cutting timeline enormously. And that helps us to basically go to where we would like to go in terms of all the improvements we need to do. So 5 ultra-cold strontium labs were built in less than 18 months. And this is in large part because of what we know from the HEP production methods in which we are applying this to this kind of infrastructure. That will not only be important for that project, but we have lots of inquiry now coming from quantum computing systems, because they're suffering from the same problems, because at the end of the day, they all need laser stabilization systems, they all need ultra-high vacuum systems to be built, and they would like to do that obviously in the most efficient and shortest time scale. So now there is a production line being set up, and that's also something we could offer to other countries if they have an interest in to participate and work with us. We can help with the building of those systems if there is any need for that. Now, back to the landscape. Ion and matches, we have already heard about ion and matches. By the way, ion and matches are direct partners. So we have directly partnered with the matches experiments in the US. We're making actually money contributions to matches itself. We are several institutions which are also in ion. So that is obviously one part of large-scale interferometer prototyping, but there's much more ongoing as we speak now. So there is, for example, a 100-meter detection system. This is now not built horizontally, but is built vertically with a 2-arm structure traditionally, but based on quantum sensors and atom interferometry in France. Similar projects are happening in China, and there's a tower system also in Germany. Each of those 5 are financed at the moment with 10 million currency units. And they're currently ongoing. So this means we have a global effort of around 50 to 60 million currency units invested in atom interferometry to be developed for fundamental physics exploitation. So these are all national initiatives, not on an international ground yet, but national initiatives, which now need basically to be put together into a more international scheme to really understand how to move forward with all this prototyping and what the best way forward is. And this brings me to an advertisement. So with John Ellis and myself and many out of the cold atom community, we're organizing a terrestrial long baseline atom interferometer workshop at CERN. And that is really the idea to bring together all the stakeholders, fundamental physics stakeholders, but also cold atom stakeholders, whoever has an interest in this long baseline atom interferometry, to discuss the options of where and how we could build large-scale atom interferometers across the globe. And that is now starting to build a community effort that can basically go along this. And I'm inviting you to have a look at this workshop page. So the workshop will take place in March 13 and 14. And there's also registration for those who would like to come to CERN. But there will also be an online option to join via Zoom eventually. So that is going to come. Now, just to show you that CERN is not only being chosen just as a random place and it's a good place to come together, but CERN is also one of the potential sites of hosting a 100-meter atom interferometer detector that's been summarized here in this slide. We're working very closely with the Physics-Born Collider team, but also with the Quantum Initiative to investigate what the options are. And there are other options in Europe, like, for example, the Bulby and Dasbury mines in which these things can happen as well. And just to show you, if you look and compare, for example, with FNAL, where matches has been built, CERN sites for basically, stochastic measurements and the seismic noise, they look very, very comparable. So these are all good places in which we could build these detection systems. Ideally, we would like to have 2 of them, if not even 3 across the globe. And again, just to point out that even with a 100-meter detector, and that's already in a time scale of 2030-ish, what we are planning for, we could open up a first new frequency range for gravitational waves. So with the sensitivity I mentioned to you already, this shows you what LIGO and Virgo and advanced LIGO and Virgo eventually will be able to cover in that frequency range. But with a 100-meter detector, either in the US or in Europe, or even combined, that would be even better, you can open up a completely new frequency range, as I will show you in a minute more. So a 100-meter detector by itself has already quite some interesting applications to gravitational wave physics, and even more so ultralight dark matter. So that brings me now to the real science motivations for these experiments. And 10 more minutes. Yeah, it's fine. To the science motivation. So it's the pathway to gravitational mid-frequency. And that basically shows you now this the frequency versus their characteristic strain of where we are basically today. If you look at that plot, you can see this is LIGO, what I showed you before. So there's a potential, extension to LIGO, which we call Einstein telescope, if it then's been realized. And obviously, LISA has been approved and is going to fly in 2035. Now, if you look at that plot, you can see that there is, as we would call it in London, mind the gap, a significant frequency gap in which we have no experimental solution at the moment to measure gravitational waves. And that has been the gap in which we have been pitching basically atom interferometry for, because a kilometer detector already, and that's been shown here, a kilometer detector, which we could have by 2035-ish, so it's similar timelines with LISA, could start filling in this intermediate frequency range quite comprehensively. And that is already very interesting. Now, there's much more to this mid-frequency band than many people do appreciate. One important aspect to it is that all the signals you are basically observing in that mid-frequency range have typical lifetimes of days, hours, days, weeks, or even months. So that's the frequency range you're covering. Now, if you think of LIGO and Virgo, you only see the last chirp of this black hole mergers. So it's a really, really short signal. So anything you would like to do in terms of multi-messenger physics is really a challenge. However, if you have a signal that lasts days, you can actually utilize the rotation of the Earth around the sun in order to make sky locations, for example, of black hole mergers. And this has been shown here also by Jason Hogan, but also has been verified by our groups. For some of those signals, we would have got ideal sky locations. So if we would have had a mid-frequency detector instead of a high-frequency detector, then basically we could have already said weeks before that there's a signal coming, do your multi-messenger physics. That will be a major advantage of doing physics in that mid-frequency range once we have these detection systems being put in place. And for that reason, we are really working very closely also on a tandem solution between ion and matches, as I pointed out to you already, with several of these atom interferometers which are actually operating in sync. That is one of the goals of the project, which we're currently setting up, synchronous operations between atom interferometers in the US and in the UK. So that's going to come. But ultimately, and that's what we have proposed to ESA, ultimately you want to bring this to space. And there's many reasons for that but the simplest one is interrogation time, because you have to have free fall. And in order to have infinite free fall, you have to go to space. Now, when you go to space, then obviously you can also push the distances between your atom interferometer sequences even much further, hence increasing the sensitivity enormously. So that has been submitted to ESA in the Voyage 2050 call, and it's currently still under evaluation as a potential thing that might be flying in 2045 or even longer. So more than a decade after LISA, obviously. And that's then how such an experiment can look like in the mid-frequency range. So already a very simple experiment, basically based on that, can really cover completely in space the mid-frequency range. And then, and that's the ultimate scenario which you can have, and this is, I'm talking here about 2045, for various different incarnations of space-based and ground-based experiments we could potentially build at that timeline. This could be the gravitational landscape plot you're looking right now. So if you compare this with the one we had before, there would be enormous progress forwards towards the full coverage of the frequency range. So that is obviously still more than a decade away, and I want to point out this is not competition with LISA or Einstein telescope. These experiments will happen before we will be able to do this exploitation with atom interferometry. So it's, if you like, the next generation after laser interferometry, which we're planning here. Not to go too much into the details because I'm running out of time. Basically, just to point out that obviously it's not only about astrophysics. I mean, black hole mergers, it's fascinating, it's interesting, we weren't going to learn a lot about it, but there's a lot of physics that must have happened at the beginning of the universe, which still has led to gravitational waves. And some examples we have been summarizing. One interesting one is the first phased order transition. And if you now look at these models and how gravitational waves they are producing, you see they look quite different than the ones we were showing before for the black hole mergers. And in order to separate such a signal from the one which from black hole merger, which would go like this, you will have to be able to measure over a very long distance in frequency the signal itself. And that again is the argument of why you have to have full coverage of the frequency range, because only then we can separate signals coming from gravitational waves from cosmology background or from astrophysics background, if you like. As another example, so there's another example here for cosmic strings, which again make the point that you really have to have full coverage in the frequency range. There's much more information in a paper John Ellis and myself have been writing, and others collaborators if you've been interested in. Very quickly to ultralight dark matter, because that's also fascinating and it's on the way to gravitational waves. So it's really in that frequency range. So this is a range I have been exploring for more than 20 years myself, WIMPs in particular, with other people's like Sven Heinemeier and others, and now this is a new range, we're looking into it. And it has already been pointed out that this is a huge parameter space which is unexplored. Atom interferometry can take some part of it, but clearly not all of it, and it will have to be a comprehensive program to cover this completely. And just to point out, we mentioned this already, this is classical waves basically, and let me go straight to the limits, just to show you that in this parameter space, again, the sequence of different experiments we could set up over the next 2 decades, like the terrestrial experiments, but also some of the kilometer scales and space-based experiments will really be able to probe, you know, really orders and orders of magnitude of this parameter space as we go along. So it's a really interesting program we're having here. And I only were touching on basically, you know, gravitational waves and ultralight dark matter, because these are the 2 main drivers we are developing. There's a lot of other interesting science you could do potentially with these atom interferometers once you have built them with that level of sensitivity. A very interesting one is namely now looking at probing dark energy, in particular placing limits on the gravity mass. So that is an active research we are building up right now, and we would like to make that case as a 3rd leg of the physics case, if you like, in a year's time from now. That is very encouraging things you could do with atom interferometer, also when it comes to not only probing dark matter, but also dark energy. So it's a really exciting new research avenue ahead of us. Yeah, and I'll leave it here.
Thank you, Oliver. Thanks a lot. Okay, questions? Yeah.
Hi, very interesting. I have 2 questions. First about, you said you can determine the location already beforehand and then tell the other instruments where to look at. But is it really sufficient with 2? Because I think with LIGO Virgo, only once they got 3, they could really pinpoint something.
Obviously, it will be better to have 2 on Earth, but that is not where the sensitivity comes from. The sensitivity really comes from basically the rotation of the detection system. It could be 1 or 2 of Earth around the sun, because the signal you are measuring is not just a chirp, it's really something that goes over weeks. And
Okay.
while you go around, you can basically make sky location with the sun.
Okay.
Yeah.
And then on page 32, where you are showing this physics example, the mass scale lambda that could be accessed by your experiment, by the various experiments, actually, it's very slow. Yeah,
I know it's.
I suffered the same. And I was wondering why the improvement is so low. I mean, you go really from short to large experiments. And one more.
It's the same here, I think, but okay.
Okay, yeah, for this lambda scale, yeah. I mean, the improvement is really 10% or something like that. And I was wondering, why is it so bad?
The scale here on lambda here?
Yes, I'm also in the left or right plot.
Well, that's probably is the better summary, because that shows you know, the limit you can really
I'm
play.
not surprised that, I mean, 700 is then completely out of reach for all our foreseeable future. And
yeah, I mean, I don't know. That's a model. Like John would be better, but he's in another meeting now. But John would be better to explain that because he has done that with his student. I don't know how this lambda translates then basically later to the other mass scales. But yeah, that's basically what comes when you have that particular implementation of a very simplified first order. There's several more in the paper I was pointing you to. Have a look in there. But yeah, ask John why it's only such a small problem.
Thanks.
And there are many people written, not just John, there are other papers on that too. But we have two questions. So Vivek is one, and then there is Sadiq. Okay, who goes?
My question relates to the astrophysical neutrinos. Are you talking about the relic neutrinos, the Big Bang neutrinos, and how the interaction would change? I mean, how with let's say the Earth going in one direction and then 6 months later going in the other direction? What?
Neutrinos I only had mentioned in the fundamental physics shopping list, if that's what you're referring to. So what I'm talking about is actually gravitational waves that were created at the beginning of the universe. Okay. So for example, you know, after 10 to the minus 10 seconds is where you were having basically many Higgs incarnations being produced. These were leading to gravitational waves of very characteristic properties, and these are still, you know, going around. And if you be able to measure them, you are actually able to deduce the underlying quantities that must have happened at the beginning of the universe. So that's the idea. You're using gravitational waves as a memory imprint of that physics that has happened there, and you analyze it later.
So it's not directly neutrinos. It's
not neutrinos at all.
It's just a gravitational wave. It's the wave itself that was created with that particular phase order transition or anything else that has happened there.
All those physics leads to tensor perturbations of space-time, which create space-time, and that's what he's talking about.
And all these gravitational waves are still there. We just need to be able to be sensitivity enough to measure them.
So it's a direct measurement of metric fluctuation, not to light or polarization or neutrinos. Anything, it's a direct measurement. Okay, Sadiq had the last question. Then
so this is kind of question in 2 parts. One is the characteristic strain that you have with at these frequencies, which are essentially longer time measurements, that is smaller than the what LIGO supports. And so is that competitive? A, and the other thing is that if you have a longer time over which you have to integrate your signal, you will have a lot of confusion from different signals which will pile on. So how do you intend to resolve that? What is the science case for that?
Okay, first question first. So you might have realized that I switched scale. I had not enough time to explain this because before I showed you strain sensitivity as a function of frequency, and now I moved to another quantity, which is basically a dimensional quantity, it's the energy density of a gravitational wave. The problem with the strain is, depending on the sensitivity, it may look like that an experiment is actually not so sensitive. LISA is even worse than the mid-frequency, but it's just a property of the density of the gravitational wave, energy density you're measuring. So if you look here, actually, LISA is better in the peak sensitivity than Einstein telescope, because that's the real quantity you're measuring. You're measuring the energy density of a gravitational wave. The strain is simply a translation into it then later. And you just get a larger strain at higher frequencies than you get at lower frequencies for the same energy density. Energy density is a much better way to compare, in my opinion, but then we can argue with the gravitational wave people because this is historical, so I'm not going to do that. But from a physics perspective, that's a better way to do. Second, you are absolutely right. So once we are building experiments like LISA in particular, because that will be exposed to that, you will measure, hopefully, a real magnitude of different gravitational waves happening all at the same time. And we will have to establish the analysis techniques to basically filter them out individually. Now, LISA has huge working groups currently working on that because it's even more important for them than it is in the mid-frequency, because as higher you go, basically, as more of those signals you're basically getting, yeah? So that's what LISA is doing. And at the moment, we are parasitically hoping to benefit from whatever LISA is basically developing. So we are aware of it, but we have not the bandwidth right now to build up our own analysis team. But LISA has a lot of people working on that.
Okay, let's thank the speaker and wonderful talk, Oliver. Thank you. Very comprehensive. So come back here at 7:15 for the cultural program. The interesting Indian Odissi dance on a very interesting topical theme. So thank you.